Today we're going to talk about privacy threats, anonymization, and consent. So by the end of this module, you ought to be able to identify 4 different kinds of privacy threat and give examples of each. You ought to be able to define k-anonymity and explain why it's both useful and insufficient as a privacy guarantee. This third point I've decided to make more optional because it's a little bit advanced, but I want you to be able to at least ideally explain the intuition behind differential privacy, although again this is optional. I'd like you to be able to apply basic pandas operations to detect quasi-identifiers, which we introduced in the previous module on fairness, and check for a table for k-anonymity violations, and evaluate whether a proposed data sharing plan satisfies key consent principles. So privacy has slightly different but varying definitions, but generally it has to do with a person's right to control information about themselves, including who can see it, how it is used, and for how long. And for many years, privacy has been under a tremendous amount of threat from various organizations. In data science, privacy risks arise at various stages of the pipeline, from data collection in the first place, to how it's stored and cleaned, how it's analyzed and modeled, how it's disseminated through publications and other forms of sharing, and then how it's potentially reused by others for downstream tasks. One key insight is that a data set can technically be anonymized at collection time, but still have private information within it that's recoverable when it's combined with other data or when another model is trained on it and queried repeatedly or used for predictions repeatedly. So there's 2 misconceptions that we want to try to dispel. The first one is, well, we deleted the names so it's anonymous. Names are very rarely the only real source of identifying information. And second, well, we used a public data set. We used the datasets library in Python to get an open data set, so there's no privacy concerns. But again, you could combine public data sets with other data sets and still use them to expose private facts. So these are the 4 privacy threat types I mentioned a moment ago: re-identification, linkage, inference, and aggregation. And each of these have their own forms of attacks. So for re-identification, the idea is, well, there's a record that's been de-identified, information's been removed from it, now it's private, but we can still match that record back to a specific person, or maybe a couple of people. We'll talk about that in a moment, how that's basically almost the same thing. There's this paper by Sweeney, actually precedes this work technically, but Sweeney showed that 87% of Americans can be uniquely identified by a combination of their zip code, which is like a postal code, their date of birth, and their sex. A linkage attack is when 2 separate safe data sets are joined together to reveal sensitive information. So if you have Netflix ratings and IMDb public reviews, then you can infer political views and even sexual preferences from those data sets. I should include a link to that also because this is a real example. Inference attacks are when a model's outputs can be queried to reconstruct the training data. There's a whole topic area here with deep learning and highly capacious machine learning models. But for now, just take it as read that if you can look at, say, generative models that produce images or produce text, sometimes that output of the model can be used to infer whether or not a record was in the training set that was used to train the system in the first place. And an aggregation attack. So it's when many individual harmless pieces combine to reveal something sensitive. So name and employer and neighborhood and commute time can reveal your home address. This is to be, it's very similar to but different than re-identification. So each of these 4 threats can occur even when you have a single data point, and that data point doesn't look to be sensitive on its own. We use ancillary or outside information, and it can be used to turn that single innocuous-looking data point into something potentially hazardous. This matters for us, responsible data scientists, because we don't need to be a hacker to cause a privacy violation. I use the word hacker, but historically hacker usually had positive connotations associated with it, someone who fiddles with things, but I'm using it in the silly modern way to mean someone who's like deliberately trying to break a system for nefarious purposes. So you don't need to be what we might call a cracker to cause privacy violation. That word also has other connotations to it. I'm not going to touch right now. If you release a model, if you share a summary table, and you publish a notebook, your exploratory data analysis notebook we talked about in a previous module, if you publish that on GitHub as part of your experiment, everything can look good line by line, but it can still enable each of these attacks. So literally trying to do the right thing and going line by line independently, and not finding anything threatening can still potentially lead to problems. So the point is to try to be paranoid within reason, but not more paranoid than that. So here's another anti-example. You and I anonymized some data by dropping the name column, and maybe we were lazy and we didn't realize what we're talking about in this class, so we missed something important. So imagine we're working on a health team, and we're looking at patient data, and we want to share patient data externally for some reason, or at least to some other group. So, whoops, spelling mistake. So the reason was we removed the name, the social security number, and a phone number. So we think those pieces of information are too specific to the patient. By removing those columns of information, now the data set is anonymous for whatever that means specifically. But imagine we still have other information. We have age, we have zip code, this should be postal code, I'm sorry, diagnosis, employer. Diagnosis, lots of people have anxiety disorder, and lots of people work at Dalhousie University, et cetera, et cetera. Lots of people are 34 years old, et cetera, et cetera. So we release all of these things because each of these data points, with a slight exception of zip, I guess, or postal code, is fairly innocuous on its own. But age and the postal code and the employer code form a almost unique fingerprint for many, many of these rows. An attacker with access to the university directory, so maybe we find we have the university directory. We can narrow things down by age. Maybe we don't have the age exactly, but we can narrow down to a set of people in their 30s. We can further break things down by, we may know where someone lives, maybe not at the exact postal code, but somewhere nearby, like what neighborhood somebody lives in. Maybe we have access to phone records or social media in addition to this data set to be able to further narrow down this list of possible people to whom this row might represent. And eventually we end up with, there's only a few people who are 34 and live in this neighborhood and work at Dalhousie University. So I know from this table that one of these 4 or 5 people has anxiety disorder, and maybe now I'm going to try to take advantage of it. Or certainly if you have other diagnoses that might be more, carry a greater social stigma, like HIV, then maybe this malicious person could try to take advantage of it for their own advantage, obviously not for the attackees. So indeed, the attacker will learn the diagnosis. Sometimes when you have regions like Nova Scotia, some FSA age employer combinations are going to be very unique just to one individual people. Never mind, we don't have too many 50-story apartment buildings here, so knowing the postal code might be highly indicative of the person. So removing name, SSN number, phone number, obviously necessary, but it's not really sufficient. Necessary but not sufficient. And quasi-identifiers, so identifiers that mostly look innocuous on their own, can, when combined, still narrow down a list of possible individuals to individuals. And that's the problem. That's why this is the anti-example. So a little bit more math. These quasi-identifiers we just talked about. So a quasi-identifier is a set of attributes Q. There's K of them, Q sub 1, Q sub 2, all the way up to K sub K. We had 3 of them really in the last example. That in combination can link a record to a particular individual, even though none of the attributes themselves is a direct identifier. Many people live at that postal code, many people have that age, etc. So this is why it's dangerous. This is a bit of a counting argument. This is a bit of a pseudo argument, I guess. Imagine you have a population of n people, and each attribute q sub I has d sub I distinct values. This is the number. This is the number of possible ages that exist. These are the possible neighborhoods that exist for the postal code identifier. If the attributes are independent, then the number of possible distinct combinations will just be a product of each of these possible values, multiplied over k factors. So if you have 3 attributes, we have 100 age values, 900 postal codes, and 30 employers that exist in this data type, for example. Then you'd end up with about 2.7 million possible distinct combinations, which is more than the population of Halifax, even the population of Nova Scotia at the moment. So most people in a real data set can be uniquely identified by only 3 or 5 of these quasi-identifiers. There's so many possible combinations that could exist of all the possible combinations, but only a small proportion of them actually do exist. And that kind of difference is what kind of matters here. And this is where the Sweeney's work showed that like a huge proportion of the American population, which is the country to Canada's south, can be uniquely identified using only the postal code, the date of birth, and their sex. So Sweeney also introduced the idea of k-anonymity with respect to a set of these quasi-identifiers. And the idea is that a data set satisfies this condition, k-anonymity, if every record is indistinguishable from at least k-1 other records given these values of q. So there's like an equivalence class. All of these rows of the data set are all equivalent to each other. They all form an equivalence class that are defined by unique combinations of these q values for at least k records. So here's an example for k equals 3. We have, there's 3 people who are aged between 30 and 40 who live in the postal prefix B3H, which is in Halifax. And for these 2 q values, age group and postal code, there's at least 3 people that fall into this category. So the first 3 rows here share, the same QI values. So an attacker can only narrow down, these rows to net 3 people. So we have 3 people. We know that one of them has anxiety, one of them has diabetes, one of them has hypertension. We don't know which is which in this set. This is a pretty small set, so it's a pretty cartoonish example for the purposes of this class. A motivated attacker can quite easily narrow this down any further, but for the sake of defining k-anonymity, indeed, there's 3 anonymity for these 3 rows. So there's a couple of techniques to achieve this. So one of which is to suppress information. So remove any row that can't be grouped with k-1 others. That's the first one. So just if one person, like one row of the data, is unique on their own, and there's only one particular combination of this age and this postal prefix, then that's too specific. We're identifying this person, so they have to be removed from this data set entirely. Delete that row. You can generalize, so you can replace specific values with ranges. That's what we did here already. So instead of having actual ages and years, we had ranges of decades. Similarly, instead of having exact postal codes, we just replaced that with a postal prefix, which still might carry useful information, but it helps to generalize things and abstract things a little bit, so the rows appear more similar to one another. Now, this isn't enough. It's good. It's a good thing to know about and to consider, but it's not good on its own. The first weakness is the homogeneity attack, and this is described in this paper. So if all records in an equivalence class share the same sensitive attribute value, knowing that you're in that class will reveal the sensitive value. So here, the attributes that are in our set Q are age group and postal prefix. We have these 3 rows all have the same age group and postal prefix, so they're k-anonymous with regards to those attributes. But each of these 3 people have HIV/AIDS. So even though you're not exactly sure which of these 3 people these rows refer to, you can know with certainty that they have HIV. Similarly, like this is stretching things a little bit. If you have, say, if you're doing k equals 10 anonymity, so 10 anonymity, you have 10 rows, and 8 of those 10 rows have the same diagnosis. You're not guaranteed that any random person derived from this set has this diagnosis, but you can, to some extent, say that you're 80% confident that they do. And then if you're going to call them up, or if you identify them in some other way, and assume that they have this diagnosis, then most of the time you will achieve in your aggressive attack. When I say you, of course don't mean you, because you're a good person and you would never do that, but you need to get inside the heads of these attackers sometimes. So yeah, even though we've achieved k-anonymity, knowing that we're in the group, it identifies the diagnosis, so it reveals information, which is, again, like leaking information is sort of the challenge we're dealing with in this module. L diversity, also described in this paper, can fix this, where every equivalence class must contain at least L distinct values of the sensitive attribute, in this case the diagnosis. The second problem with k-anonymity is background knowledge attack. So if an attacker knows that Alice specifically lives in B3L and is 55, then all 3 records in that K class have HIV. So we've gone a step further and we've re-identified this particular person as having this particular disease. This is an example of when we have 2 data sets and we can combine them together to re-identify someone in a data set which on its own seems to be anonymous or private. So T-closeness, defined here, goes a bit further. The distribution of the sensitive attribute in every class has to be close to its distribution in the whole data set. So there's no difference between a particular subset obtained by segmenting the data in this way and priors that exist overall in the data set. So your chances of identifying a group of people who are more likely to have HIV, the probability within the data set of someone having HIV is no different than what it would be in the entire data set. So there's no difference. We've obtained nothing. When the attacker has obtained nothing from kind of trying to break this anonymity function. So for this course, the main takeaway is that k-anonymity is very useful as a baseline concept, and it's important for you to understand what the concept is. And it's a fairly simple concept to understand. We have the idea of quasi-identifiers, which we have made as vague as possible and as general as possible beforehand. And k-anonymity basically just refers to the idea that there are at least k rows of data in our data set with the exact same generalized quasi-identifiers in it. Super simple concept. We know that it can be broken. Again, like everything, there's always caveats in data science and machine learning. There's always corner cases. And in particular, when you're thinking of impactful concepts like privacy and bias, it's always a good idea to be especially wary of possible leaks or possible breakages in your techniques in order to not be overly confident in them. So in practice, in production, we don't see k-anonymity too much. We see differential privacy, which is a little bit it's deeper, it's a bit more complicated, and as such, we're only going to introduce it for your own benefit, but we're not going to necessarily keep it as part of the evaluation of this course. So this is an aside. The informal idea is that a computation should be, we can call it differentially private, if the output of the computation, a prediction from a model, for example, will look nearly or exactly the same ideally, whether or not a single person's data, your data or my data, was included in the data set or not. This is related to the inference attack I mentioned in those 4 types of attacks previously. A model makes a prediction, I can look at the output, and then looking at that output I can be like, oh, this person's data was part of the training. And therefore, knowing that would expose a lot of other possible attacks. The formal definition, that goes back to even before it was really even named differential privacy, but it basically means you have this randomized mechanism M. This could be a model, and it satisfies epsilon differential privacy if for all data sets D and D prime, these are 2 different data sets, the only difference is one record is removed in one record or one person's records are removed from one. Then for all possible outputs, S, the probability of that output will be within a certain range, whether or not you have those records in the data sets or not. So what's going on here is saying, well, given this data set is used to train a model M that is making predictions, and some of the predictions are among the set of possible outputs S. So I'm making actual predictions, you can see, in a training set or a validation set or a test set, but this is supposed to hold across any possible outputs, even the ones I haven't seen yet. And if the probability of a possible output, like an image being generated, for example, or a text being generated, its probability should be less than or equal to the probability of, the output from the same model trained on a same but one data set, multiplied by e to the epsilon, where epsilon is a hyperparameter that controls how private the model is. Okay, so in other words, these probabilities should differ by an amount that is arbitrarily small, and the smallness of that arbitrary range is determined by this quantity epsilon. So small values of epsilon here means strong privacy. The outputs between the model trained on dataset D and the one trained on dataset D prime should change almost not at all. If the one person is added or removed from one dataset or the other. Larger values of epsilon will give larger values for E, and therefore it will present weaker privacy. There's more budget, there's more range in which the output can change, so the probability of an output from one model trained from D will be maybe potentially quite a lot different than an output from a model trained on dataset D prime. So ideally we want the differences in probability for all of the possible outputs for these two models to be as close to each other as possible. And if they're very close, then essentially you and I or anyone else is unable to tell whether or not your data has been included in dataset D or dataset D prime. That's the underlying idea of all of this. The mechanism is a little bit complicated, again, beyond the scope of this class, but just to tease it, you're going to see this potentially later if you get more into responsible AI, responsible machine learning, to privately release a numeric query, a function of D with sensitivity delta F, which is the maximum allowable change in F. When one record changes, you have to add noise. So we have a model, we have outputs like a numerical query of a function based on D. We basically add noise to the model. So the model becomes noisier according to some proportion epsilon. This is way too advanced, I think, for where we are in the course right now, but I wanted to mention it anyway. This is going to be online for free, so it's very important that you at least know the differential privacy exists. In the real world, beyond this class, it's good to know like the core idea, the intuition about like the probability of outputs, whether or not a particular record was included in the training set. And it's also helpful to know to some extent that the way we achieve this is by adding noise to the model. So we kind of adjust the parameters of the model in order to kind of add noise that washes out this uniquely identifying information. So I want, again, this is not an exam formula. You're not going to be asked on it in the exam. You're not going to need to derive any of this, but I just like you to, for your own benefit, going forward, knowing that adding very careful noise can determine to what extent one person's data can change the response of a prediction. So again, because we're not really going to evaluate you on differential privacy, then this slide is also going to be it's going to inherit the aside attribute of this of the previous slide. The idea is this: k-anonymity basically predicts whether or not you're a member of a group or not, and epsilon differential privacy protects whether any individual was in the data set at all. K-anonymity is achieved through kind of thoughtful generalization of these quasi-identifying variables by suppressing information in the data set as well, whereas E differential privacy or epsilon differential privacy involves adding noise to the model, carefully calibrated noise. So is k-anonymity composable? Can we kind of can we add kind of components in series together? K-anonymity doesn't really provide this, at least not that I'm aware of. There's not any works that suggest that two k-anonymous data sets can be combined and for the results to also be k-anonymous, whereas epsilon differential privacy budgets do actually add up, so they're composable and combinable in a way that extends and generalizes and is combinable. Linkage attacks, k-anonymity can, to some extent, sometimes handle linkage attacks, but I wouldn't recommend it, whereas epsilon differential privacy, by design, handles linkage attacks. Again, I mentioned a moment ago that there's always caveats, and in fact, even one of the students in our research group here at Dalhousie showed that even differential privacy is circumnavigable if the right conditions are met, so there are ways to reconstruct some data in very particular circumstances. K-anonymity is sometimes used in legacy systems. Sometimes it's used in health data that is protected through other means, like data governance means and that sort of thing. But in production, epsilon differential privacy has been deployed by companies like Apple and Google and the US Census Bureau. I think it was quite easy to explain k-anonymity, so therefore it's good for use in a class like this. Differential privacy is a bit harder to explain, and it does require some probabilistic arguments, and this would be something more for you to see again in third or fourth year of your computer science degree. Here are some references to the real-world deployments I mentioned a moment ago of differential privacy. So generally, differential privacy is the gold standard for how to anonymize a model more than a data set. So actually, these are kind of also solving slightly different problems. K-anonymity is usually applied to the data set, and differential privacy is applied to a model. But there we are. A couple of work examples. Can we detect quasi-identifier risks in pandas? So here's like a fictional toy example where we have our postal codes, our employers, our diagnoses. We count the equivalence classes. So this line is actually kind of important. This, from lines 26 to 31, is the section where we group by the quasi-identifier columns, and then we count size, and then we reset the index based on size. So basically what we're saying is, given these combination of age group and postal code and employer, group these together, and then form unique, these three labels become one label through their conjunction, and then count how many data points or rows fall within that conjunction, that new label, which is determined from this size, call to the size function on line 29. So we see, I guess, the explanation of these equivalence classes. There's 144 of these labels, which are the unique labels conjoined of these three other variables. There's 144 of them. In some cases, there's only one. Actually, even at the 50th percentile, at the median, if we sort all of these equivalence classes, at least half of them have only one unique data point within them. And in fact, the 75th percentile, has two or fewer data points in that equivalence class. And indeed, there's only 135 out of the 144 in this toy data set. You can see how I produce it here. It's randomly generated. Only 135 out of 144 have k-anonymity less than 3, which is already kind of small, even for this toy data set. So, this we can very easily re-identify people. So again, for many equivalence classes, so for many possible unique combinations of these three quasi-identifier variables, we only have one or two individual members in them, meaning that these rows are uniquely or almost uniquely identifiable, even in this very simple toy use case. So that can be a challenge. Here's a visualization of what we have. These are the equivalence class sizes and the number of classes within them. So actually, I should have changed the X labels here, but yeah, they have. This shows that many classes have only one element in them, and a fair number of them only have two elements in them also. So these individuals are either uniquely or almost uniquely identifiable. The right plot, basically, you can check the code, removes, coarsens the zip or the postal code from 3-character to 2-character prefix. You can see this yourself here. So it makes things a bit less specific, which can sometimes harm overall performance of a predictive model or predictive algorithm, but it's made things a little bit more private using k-anonymity. And we've improved things a little bit. So the number of classes violating k equals 3 anonymity from the previous example was 135. And we brought this down to just 35 if we just removed the last character from the postal code, from the 3-character postal code in Nova Scotia. Every time we generalize, every time we make things a bit more abstract or coarse, we trade some utility, so less precise data, for some privacy. We're not using this data for prediction at the moment, we're just talking about privacy, but like we're removing some information, and whenever we remove some information, chances are that the model will become less performant overall. But that's a trade-off we've made in order to increase privacy, as you can observe in this graph on the right. So indeed, there's no free lunch. The no free lunch theorem applies over and over again in various aspects of data science. At some point, if you keep on abstracting, the data becomes so coarse that you're not going to be able to actually use it for anything useful in the real world. So the right trade-off between privacy and utility depends on the purpose, the population size, the legal context, other safeguards you might have around the data and the model. Maybe only a certain number of people can have access to the data and the model within your organization. So just having the K threshold by itself is only one small piece of the puzzle. This is a side note, really. This is because it has to do with differential privacy, but this basically simulates adding Laplacian noise to a differential privacy mechanism. So these are different values of epsilon. So we talked about epsilon being basically controlling the privacy budget that we have available to us that allows us to differentiate between the predictions of one model versus another based on whether or not a particular entry was included or not in the training. So we have different levels of epsilon, we have different noise scales, and these graphs basically show the difference between, we have smaller epsilons, which mean more noise, which means stronger privacy, but less overall utility. And these graphs basically show the released counts in terms of these histograms for these scenarios. What's useful here, at epsilon 0.1, which is relatively strong privacy for this toy example, the standard deviation of noise is about 14. So for a true count of 18, the released data would easily be for 32. So an attacker will learn almost nothing specific about an individual, but for weak privacy, so if we set epsilon to 5, we have a much greater privacy budget. Noise will be about 0.28, according to that function we talked about in the previous optional slide. This will be almost identical to the true nature of the data, the actual data. So this is high utility. So the model is a good representation of the true data distribution, but now an attacker can more reliably infer membership within a group. So this is an example of the trade-off between utility on one hand and privacy on the other. And this shows that this trade-off is explicit and it's tunable through this particular parameter epsilon, or I guess hyperparameter epsilon. So this is the differential privacy's advantage. One of differential privacy's advantages over k-anonymity. You can formally state what the privacy guarantee is that we're providing. So with k-anonymity, it's sort of like a little bit of a hack. With differential privacy, there's all kinds of theoretical bounds as to the extent to which you'd expect the data to be identifiable or not. So jumping out a little bit back into the area of governance outside of pure data science. Consent is very important, and it's important in various aspects of life, and it's also important in data science. This is the process by which an individual will agree to the collection, use, and sharing of their data with full understanding of what they've agreed to. So a lot of your data, it won't shock you to know, has been gathered without your consent and is being used for all kinds of purposes that you did not agree to, which technically violates a lot of legislations and regulations. There are various properties of valid consent drawn from the European Union's GDPR and the Canadian PIPEDA and tons of academic work on bioethics and standards. So even NIST published standards on what constitutes informed consent. So informed is in the name. What does informed mean? It means that the individuals from whom data is being collected, they understand what the data is collected, what data is being collected. They also understand how it's being used. Sometimes these like PIPEDA and regulations and legislation like it can be a little bit vague and open to interpretation. So what does it actually mean that you understand what data is collected? What does it mean that you understand how it's going to be used? Understanding also will need to be defined as another property, but that's usually left to precedent and legal systems that are beyond the scope of this class. Voluntary, so you shouldn't be coerced or penalized for refusing. Now, there's a ton of ways in which websites might, coerce you into involuntary giving up your data through means like they call it dark patterns, like emphasizing one button, I agree, versus de-emphasizing another button, cancel. Technically, you might have an off-ramp to not give your data to some of these companies, but it's kind of hard not to, or for people who aren't really paying attention, it's just naturally the default thing to hand over your data. So is that voluntary or not? That also opens up all kinds of legal questions that are beyond the scope of this class. Purpose limited, so data should only be collected for a particular purpose and not used for anything else. So, if you have health data collected for research and somehow that makes its way into a company that's using it to build advertisements, that would be a violation of this form of informed consent. Time limited basically means that the consent can be withdrawn. So I consent to giving the data to you now, but for this to be valid, I should be able to withdraw my consent at any time, which means that you need to delete all of my data and you need to show me that you've deleted the data. Technically, social media websites and other data hoovers, vacuum cleaners, have means by which you can appear to request the deletion of your data, but to what extent is this actually done is again outside of the scope of this class. And granular, so you ought to be able to consent to some aspects and not others. So you should be able to opt in to your data being used for research versus ad modeling versus et cetera, et cetera. It should be not just one big consent for everything. You should be able to pick and choose some of these things. That is very rarely the case, at least in the informed consent forums that I've been part of, in particular with research ethics, but technically that's something we should be trying to include. So when we use a data set, we need to be able to ask, do the people in this data set consent to the analysis? Sometimes you say, well, it's publicly available. I found this data set on Kaggle, or I found it on Hugging Face, or I found it on some other platform. It doesn't mean that the individuals consented to its use. Usually, if a paper, like a research paper describes a data set, there's usually not only a expression that the individuals consented to their data being used, but there's actually a reference to the actual research ethics board that approved this data collection process, so that you can go to that research ethics board at the university or wherever and get information about how the data was collected, even if it was collected by others across the ocean. So consent in practice can be a bit of a spectrum, so it's not an either or thing, it's not a dichotomy. So explicit consent. So clinical trial participants can sign an IRB or an REB approved consent. IRB and REB is the same thing. Describing data storage for future sharing. Informed opt-in, so a survey platform can show a plain language summary and the user can check a box before submitting. Opting out, a social media platform can pre-select shared data with research partners, and you'd have to find the toggle and then deselect it. That might be less. So I'm kind of going from like the spectrum from explicit opt-in to like more and more gray area to pretty poor consent. Browser wrapping. By using this site, you agreed to our privacy policy. This is a lot of terms of service agreements in my estimation. This is really more of an opinion than a statistical claim. But imagine you open up like a product and then you get this form saying, by opening this product, you have already agreed to its terms. Well, you haven't had a chance to see the terms before you open the product. And same goes for websites. So, if you've already clicked on a link and it's already gathered your data before you had a chance to get the terms of use, that doesn't seem to be a good use of consent. And then, of course, having no consent at all. So just scraping public posts, purchasing a mailing list through nefarious means, inferring health status through fitness trackers or other third-party sources is just simply circumventing the whole thing and carries a lot of legal challenges for you. So a lot of the data used in our research actually sits in opt-out or lower tiers. There has been data sets that were temporarily public that were just scraped from data sets of books, for example, that had to be taken down. they're taken down only after that work gained a lot of popularity. But this happens. Users scrape the data online, they train a model, and then they get in trouble for it afterwards. But by that point, the damage has been done, and the benefit to the scraper has already been achieved. So this doesn't make it illegal everywhere. Some jurisdictions seem to be going in the wrong direction with informed consent, but that's again outside of the scope of this class. There's two principles from privacy regulation that directly constrain data science workflows. Minimizing the data, so only collecting the data that's necessary for the stated purpose. This is very common in medical science as well as lots of social science. So instead of collecting absolutely everything and filtering later, the data scientist and machine learning part of me is like, oh yeah, that's great, because we don't necessarily know beforehand what's going to be useful for our model. So we want to capture everything, capturing everything the browser, like every time the browser moves, everything in the history, to show product recommendations, store every keystroke. There's some suggestion that apps on phones can use the sensors of your phones to detect other information about your whereabouts from GPS or about what your eyes are doing from the camera. I'm not going to get into that. That seems a bit paranoid to me, but maybe. Anyway, collecting all of that data might be helpful for the utility, but obviously it's a privacy nightmare. And whereas, if you're going to make a product recommendation, really only capture raw page views and don't care too much about the degree to which scrolling is happening on the website, unless you can make the claim that it's necessary. Instead of storing every keystroke, every timing to measure engagement, every motion of the mouse, only store session duration, and so on. So instead of requesting location at all times to estimate a commute, request the location once the trip starts, when it ends, and that's it. Like ignore everything in between, if you're like a map app. Data collected for purpose A needs to not be used for purpose B without new consent. And there's a ton of violations, one of which we previously talked about in a previous module, where fitness tracker apps like location data could be used to infer the home location of people who work at a particular site, or so if someone works at the Canadian Navy, for example, and you have their tracker data somehow, you'll be able to locate them back to their house. That could create all kinds of problems. If your fitness tracker data could be sold to health insurers, if you did not agree to that, this is not really a problem in Canada, thank goodness, at least not yet, and at least not in any province. But using your personal fitness tracking data or your browsing data, or like you can imagine your credit card data, from your grocery store purchases being fed to an insurer or a credit score broker, to change your pricing seems to be something which is, again, something that most of us would not approve of. This is, I'm not going to go through all these examples because this is more for your curiosity. There's tons of examples of real-world privacy failures, including Netflix and AOL, which used to be a thing, location data brokers, even hospitals, genomic re-identification, and the list goes on. I could spend an entire lecture just going through use cases for privacy failures, but I'd encourage you to look these up yourself. Again, this is just outside the scope of the class because these are specific examples. You don't need to reiterate for me. But generally, in each of these examples, to varying extents, the data can look safe when you're looking at the data by itself, but maybe there's some other information. Maybe this other information is publicly available. Maybe there's a news article that describes a man of a rough age who had a motorcycle accident, and you happen to have hospital records from the trauma room that describes head injury for a particular range of dates. Like you can, if the k-anonymity is small, then you can re-identify that person fairly easily. So membership inference attacks is one of the main risks for machine learning models. Given a trained model and a data record, an attacker can query the model to determine whether the record was in the training set. Differential privacy, which we talked about a moment ago, still a side note for us for now, is a way to mitigate against that. But if your model was trained on private health records or private data generally, then an attacker can determine this person's record was used in the training data. That's a privacy leak, even if we never share the data, right? If the model is in public, and even if the model itself is not public but only accessible through APIs, Just polling, making various polls like through APIs to that model can still be used to get a distribution of performance, and then you can use an individual's actual data point to determine whether or not that data point was part of the training set. That's membership inference attacks. That's saying this person's data was a member of the training set. Model inversion and data extraction. This is basically, again, querying a model, even just through APIs, through a black box approach to the model. So the model doesn't have to live on your computer, as it usually should, but only on some server somewhere. Attackers can reconstruct approximate versions of training examples. This can include faces, medical images, or text sequences. I mean, we're all familiar with generative AI and how they reconstruct images that look a lot like real data because they actually are real data. When they start simulating or generating outputs, they become increasingly constrained by the model, which is trained on the data. So what they produce becomes more and more constrained, and what it can produce has to resemble its training data to a greater and greater extent. This is especially true of large language models. There are some mitigations against this, and thankfully, a lot of the large language model companies, two larges, have added mitigations against this sort of these sorts of problems. So, verbatim names, phone numbers, addresses are things that are more protected, but it's still, like I said before, not something you can take for granted. So I want to point you to Anne Kavoukian's Privacy by Design, or its foundational principles. She was the Privacy Commissioner of Ontario for quite a long time, and she did a lot of foundational work on privacy and data science in the world. So just like so many other things, Canada has produced some of the preeminent work in these areas. So these are 7 principles. I don't expect you to memorize all of them, but try to get a handle on some of these. So be proactive, not reactive. So anticipate and prevent privacy events before they occur. This is similar to my invocation to be somewhat paranoid about your models, to not be overconfident in them. Privacy should be the default. By default, the expectation should be that you require fine-grained informed consent from your users. It should be an opt-in process, not an opt-out process. So the default is privacy. Privacy should be embedded into the design. It's not something that happens after a lot of the modeling, but it's part of the design from the very beginning. So the data modeling, architecture, the pipeline you're using, any kinds of pre-post infra processing, privacy has to be part of the conversation. Privacy and utility, even though they are often at odds with one another, there are some trade-offs. The trade-off isn't zero-sum. So there are optima where you can maximize a combination of privacy and utility. Maybe one of those things is not locally optimum, but they can still be globally optimum together. Data needs to be protected through its entire life cycle, including deletion. So this goes beyond the model, but the architecture around the model, including who has access to the data, where it's stored, everything from encryption on the hard drive to multi-factor authentication. A lot of locations in Canada and throughout the world, in order to gain access to where the data are, you have to empty your pockets and leave your phone in a locker. You have to have biometric scans, so only a few people can even enter the room to begin with. So it's wonderful to see. It makes machine learning a little bit more difficult for some of us, but it's a price that we should all be willing to pay for the privacy of our citizens. Users and the general public should be able to audit and verify what data we hold and why we hold that data. And there should be ways in which they can seek that data to be removed if they so wish. It's a bit of an add-on here. And user interests are always going to be paramount when design decisions conflict. So if something's good for the company but bad for users, and something is good for users and bad for the company, then we go good for users, bad for the company, because we're ethical human beings, and that's how ethical human beings think. In general, I can't think of any particular caveats to that, but I'm sure there's some instances that might contradict what I just said, but those would definitely be the exception, not the rule. So the practical translation for this course is check where the data come from, identify quasi-identifiers, ask who can be harmed, and prefer to collect as little information as possible compared to what the analysis actually needs. This connects throughout the course, so I've kind of hesitated to include these links through the course with some exceptions. But there's a lot of concepts in this course that connect throughout the whole series of modules. So like missingness from one of the early modules connects to suppression to achieve k-anonymity. And even the imputation methods we touched on to solve missingness might also have an influence on privacy. In Module 16, we talked about encoding and feature creations. So which features are useful to us, which features combined together can jointly distinguish or identify individuals. This concept came back to us. So these concepts aren't in isolation. Descriptive statistics sometimes are just for mere reports. This is the average, this is the mean, the median, the standard deviation, the interquartile range, all these statistics we were talking about in an earlier module. Each of these things can be useful to an attacker to gain information about a data set. And tools like differential privacy are ways of protecting releases through a statistical treatment of the data in the module. We talked a lot about machine learning evaluation and how information can leak between the training set and the test set. So membership inference is very closely related to data leakage. They come from similar sources and lead to similar problems that are different. And algorithmic bias from the very previous module also interact a lot here too. So considering demographic groups, seeing who is harmed by a release of data or release of a model, and trying to apply techniques to mitigate against those are usually part of the same conversation. So privacy enforcement and bias reduction are both things we try to do at the same time. Quick note, usually when I talk about privacy and bias to general audiences, so even audiences that have less technical background as we have in a first-year course like this, I point out that there's a couple of instances where we've shown that, including our own research group, that sometimes when you increase privacy to make a model more private, that can sometimes come at the cost of increasing bias. So making privacy better makes fairness worse sometimes for certain situations and in certain contexts. That's beyond the scope of this class, and whenever I mention that, I'm always hesitant because I'm worried that someone will hear that and say, oh no, like because of this trade-off between fairness and privacy, we might as well not try either, which is obviously not the case. Just like everything else, there's going to be techniques we can use to mitigate against that particular very specific subtle problem where you can increase privacy and maintain fairness. So there's always solutions, and there's always problems too, but the solutions. Here are your quick checks. Please look at them. Here are some papers for you to read. Thanks so much for watching. See you next time.